Okay, yeah, I like yesterday I was like seeing how a lot of these talks were going, and I endeavored to cut down my slides by half, and instead I added 30 new slides. So let's see how this goes. If anybody's ever been to a talk by Anne Ferlin, my postdoc advisor, I think I've inherited her disease of stuffing too much into slides. So let's see. The one thing I'll mention is that like a huge amount of this work comes from Kate Loftus, Arthur Hugh, and Greg Alcesser. So yeah, I guess I've reached this stage in my career where I mostly present other people's work, which is, I don't know how to feel about that. Anyway, okay, so just saying things that we all know, I guess. Earth system models, projections have errors that are, to a large extent, a consequence of uncertainties and approximations in processes, right? We don't have the degrees of freedom in our model that we want to represent the processes that we want to simulate. We can kind of break this down also, right? So we have some equations, some code, some parameterization code, some schemes, and they have structure and parameters, right? So those are sort of two, we can maybe try to separate out two sources of error. Structure can be things like our choice of variables that we're using to predict. Do we choose cloud mass? Do we choose cloud mass and number? And then it could also be like the form of the equation. Do we have a power law? Do we have something else? And then there's parameters, right? So there's the coefficients within those codes. Maybe I want to fine-tune something related to snowfall rate or something like that. Of course, if you do neural networks, it kind of conflates maybe the structure is the parameters. I don't know. Okay, what uncertainties do we want to constrain? Well, this kind of depends on what we're looking at. So I'd break this down maybe three ways. If we just want to know what the atmosphere is, like how hard is it raining, that's one sort of thing. If we're looking at something like numerical weather prediction, we're in this, people have talked about this already at this meeting, so I don't think I need to spend too much time. It's primarily a state estimation initial condition problem, and there's data assimilation to do that. And then when we go to longer timescales, right, this is sort of this plot that I think a lot of people have seen. As we go to longer timescales, the sort of physics uncertainty, so the uncertainties associated with the parameters and structure of our parameterization starts to dominate. Further on, it's like how much CO2, how many aerosols are we pumping into the atmosphere, that becomes more important. Okay, and this is kind of important, right, because this guides how we address the problem. All right, and then in general, this is again probably review. We have kind of this situation where we have parameterized clouds, right? We have to represent clouds in a succinct way with fewer variables than we'd like. And then we have parameterized microphysics, right? We have all these billions of droplets, and we need to represent them with one or two numbers that represent a statistical distribution, or maybe if you're doing something like these bin or Lagrangian schemes, maybe have a few more variables. And then we have parameterized microphysics inside parameterized clouds. So Hugh Morrison calls this the parameterization squared problem. Maybe other people do too. Okay, so in general with this talk, I want to do less. I'm going to try to do sort of less of sort of all the equations and whatnot, and maybe more of sort of you know, like the manifesto, the philosophy. So yeah, please get yourself a copy of this book. It's very good. Okay, so and sort of in that line, I'll get on my soapbox and say, why do we do this, right? Why bother estimating parameters? Why not just sort of do direct ML for parameterizations? Tune onto, or constrain onto, or train on some higher resolution model for something like clouds. And I would say that one thing is that estimating and constraining the uncertainty is important. And this is sort of a lot easier, or maybe more straightforward, or maybe more interpretable with a physical model. I haven't really seen too many things that could be called plausible ML candidates for online learning. So in other words, can we actually use global satellite simulations to inform physical processes? Are there enough observations to really train the machine learning models? And especially when we think about things like extrapolating to situations where there's different aerosol outputs or different emission scenarios, right? Sort of the out of sample, the extrapolation. Thinking about something like the emission changes to shipping that happened recently. And then I haven't really seen any machine learning candidates for learning and uncertainty quantification across scales. So let's say you have laboratory experiments, right? The building a cloud chamber, can I unify that knowledge all the way up to my global simulations of clouds? So is there sort of a plausible candidate for this? I think you could maybe say, is there a plausible candidate for this for physical models? And that'd be a good question, which I will not answer. And no matter what, I think, and this is like, I think a big point for me, is that no matter what, I think a data-constrained physical model, so constraining parameters and structure in a physical model, is a necessary null test that we have to do better than in machine learning parameterizations or machine learning emulators. So it's sort of, why do we abandon the physics before we know that this other thing can actually be better? And I think it's a poor sort of null test to just say, oh, here's the standard version of the model, machine learning is so much better than that. It's like, no, well, do data-constrained physical model also.
I think we have a question.
Oh, yeah.
I mean, I've like looked at some of these parameterizations, and they just look like a neural net. They have ReLUs in them, and you know, to tune the model, you kind of comment out the ReLU you don't like, and they have parameters that you kind of like. I mean, some. I mean,
yeah. There's a lot under the hood that's pretty scary, and you know, if you talk to like microphysics parameterization people, like just ask them how much of the scheme behavior is determined by the limiters in the model, and yeah, that's what is that? That's like a ReLU function, right? You have a limit. So yeah. Yes, there's subtlety here. It's not black and white, I agree. All right, until recently, we have not had a methodology to quantify Earth system model parameter uncertainty. Of course, this isn't true. There have been papers in the past where people have done this. But the point is that I haven't done it until recently, and so that's my presentation. Okay. So what we want to do is basically estimate the probability density over parameters of interest informed by observations. So this is sort of Bayes' theorem. X is our parameters, Y is our observations. Probability of parameters given observations. The M is stuff that we're going to ignore for now, but you could think of it as structure. And then we use machine learning to accelerate this process, right? Normally what we do for Markov chain Monte Carlo to estimate parameters, we'd sample our parameters, we'd run our model, we'd compare to observations, and we'd do this like a million times. That's slow. Our climate models are very slow, so we instead do this sort of method where we first sample our parameters, run our model, and then we train a surrogate model to simulate the sensitivity to the parameters of the observations. And then we plug that into this sort of Bayesian estimation loop, and we do MCMC on our surrogate model, which is some sort of machine learning code. We use neural networks. Other people use Gaussian processes. And that makes this tractable. And then our results are sort of samples of the parameter posterior distribution constrained by observations. And we've called this for, because we need more terminology in the field, calibrated physics ensemble. And really, it's a calibrated parameter ensemble. And really, we kind of leave that physics instead of parameter there in the hope that we expand this out to cover structure at some point. OK, so we can ask ourselves, what parameters should we perturb? Right? We can think about establishing parameter importance. So this is sort of 45 parameters of our climate model, Earth system model, to those people who can't use that word. And then these are 36 outputs. So things that we could observe. And this is just sort of linear sensitivity across some range. And you can see that some are very important and some are less important. OK, so maybe we just perturb the important ones. One of the interesting things that we found is once we constrain the parameter space with observations, and then we do this again, like everything's important. So this is sort of a weird, this is an interesting thing, right? It's like, if you just look at your prior, it can give you a false sense of what's actually important. Certain things are important only in a smaller range or post-constraint. So I really recommend for a lot of these exercises to maybe not throw out parameters needlessly. OK, what about observations? What outputs? There are some things that need to be considered here, and I think this is something to keep in mind for sort of all endeavors using actual observations. These are two different products. What are these? Liquid water path, I believe. And they differ in different parts by over 100%. So just two different satellite products, and what's true? So this is kind of disturbing, but more pertinently, like how do we actually use these things to constrain our model? And so we've come up with sort of a hokey way of basically saying in between, if our model predicts something in between this and this, there's no penalty. So there's sort of no information gained if it's in between these two observations. So there's sort of things that we've had to do to sort of massage the actual observations. That's just sort of
if you look at it just superficially, I mean, they do look pretty similar.
Yeah, spatially, yeah, in terms of the spatial patterns. Yeah, that's true. Okay, and just to further iterate on this sort of methodology that we've developed, instead of, this is sort of that loop that I showed before, but one of the things that we do is we do this multiple times. So after we've done our sort of first CPE, our first estimate of the posterior parameter distribution, we feed that back in. We add it to the prior, and then we run our climate model for those new points, and then we generate a new emulator. So we actually don't refine our prior, strictly speaking, in the Bayesian sense, but we add in samples to train the emulator in the region around the prior, or informed by the prior. And we do this a couple of times, and we found that this iterative method is very useful. And it could be thought of as maybe aligned in spirit with how the CLIMA calibrate emulate sample uses ensemble Kalman methods to sort of zoom in around a posterior and then use those to train an emulator. Okay, let's see. So we've done this. This is in a paper. You can find this online. And sort of this idea of calibrated physics ensemble is that if you just do a perturbed parameter ensemble over some prior range of uncertainty in parameters, what you can get is basically a lot of values that are just completely bonkers, right? We know these aren't realistic. We know these are crazy. They're not really Earth at all. There's something else. And by doing this sort of calibrated physics ensemble, we get a sample of points. We get a diversity of parameter values across a diverse space, across the parameter space, but that all sort of agree with a large number of observational targets. And yeah, so this is sort of scatter plot of two different outputs, precipitation and long wave cloud radiative effect. And you can see these sort of different iterations, right? This black dots are our prior. These blue dots are our first round of the CP. The green dots are our second round. This is actually a case where the default parameter choice, which is this red one, was pretty good. Okay, there we go. Yeah, so the final thing I'll mention here is that basically for our perturbed parameter ensemble, our prior, 0 of the samples, zero of the 450 samples match the targets adequately. And then after doing this process of emulator-guided MCMC or emulator-accelerated MCMC, we get basically 30% of our posterior samples match after we run it through the actual model. So that's also an indication. Yep.
How do you choose the metrics? And did you ever explore, like if you left out some metrics, went through this process, does it match the left out metrics just to make sure we're not overfitting to that choice?
Yeah, that's a good question. The metrics are sort of what Greg thought were the best available satellite products. And so that was sort of done via expert judgment. There are certainly other satellite products that we could do. And we have thought about things like what if we had, and I'll talk a little bit more about later about what if we had some other observations. But I think it's a good question, and I think there's also another question of, like, we used climatologies. What if we wanted to look at something like diurnal cycle, right, that we have data for? I think those are really good questions, and I don't have an answer, but like that's absolutely where we want to go, is trying to figure that out. And I think that's a big question, like where is the sort of middle ground of what's actually useful to constrain? You're not sort of averaging out too much. Yeah.
I guess one problem I've seen with these is, what do you do with the observation, like your PPE, the observations are well into the tails or outside of the range of what your model or your surrogate is giving you?
Yeah, this is a really good question. So basically you're saying like, what if we can't match with our parameter perturbation some observation? So like, I know some groups and like like Yang has suggested just throwing these out, right? And the group at Leeds did that also, the Ken Carslaw's group that has pioneered a lot of these methods. We inflate our error. So we just inflate the error to sort of encompass that sort of structural mismatch between what you can obtain with parameter estimation. We've started to sort of play around with like, okay, does that make sense? Is that the right way to do it? What are the consequences of doing this? And I think it also relates to how you do your parameter sampling. So it's a little bit of a tricky, complicated question. Yeah, it's a really good question though. Okay, so ongoing development of this sort of methodology, we now also have started to include meaningful uncertainty estimates for the machine learning surrogate model. So as other people have mentioned, we sort of train we include the emulator error in the training. So it learns the emulator error in the training, and that is then included in the MCMC as well. So that's been something that we've been wanting to do for a long time. We finally did it, and it makes a difference. So the yellow is sort of the standard, and then the green is with the emulator uncertainty. So I won't tell you exactly what it means because I'm not sure, but it does make a difference for a lot of parameters. So it seems like it has an impact to include that. And I really think it should be included, yeah?
You're showing the 1D marginals here. Yeah. I'm curious about in the 2D space, because often the 1Ds can sort of hide structure. Did you look at those as well?
Derek wants me to look at a 45 by 45.
I do, Marcus.
That's a really good question. We haven't dug into it too much. Yeah. I think there's always a danger in looking at 1D marginals for a 45-dimensional parameter space. And there's probably still danger in looking at 2D marginals for a 45-dimensional parameter space. I think intuition really breaks down pretty quickly. Yeah. Okay, other considerations, observational uncertainties, how do we deal with structural error? Yeah, so these are some of the questions that actually came up here, right? Sampling, some people do MCMC, which is what we did. Some people do history matching, where you basically set a threshold of tolerance, and then you accept everything inside of that threshold and throw out everything outside. So there's a lot of questions here. And then how do we create a prior? So, right, our prior was just sort of a bounded uniform in a parameter space, but there's probably smarter ways to do this. And yeah, we're playing around with some of those. Okay, so moving on, what can we use this for? Let's imagine that NASA's like, hey, build a new satellite, and choose like what's the best way to build some satellite. So I think one of the interesting things here is that the ability to constrain sort of parameter uncertainty with observations, the ability to estimate parameter uncertainty with observations implies the ability to quantify the information content of an observable, right? You look at how does my parameter distribution change when I add an observation, and you say, okay, I've gained information. And so we've played around with this a bit. And so one of the things we did is that we took one of our observables, a water vapor in the boundary layer, so basically humidity, and we said, well, what if we had that same observation, but we had way worse uncertainty than we currently have? And one of the interesting things we found is that it doesn't really change anything. So none of our parameter estimates changed, which is a little bit scary. It either means that these observations are providing us with zero information, or they're providing us with zero independent information. Maybe there's some other observable that we're using that it's highly correlated with, and so it doesn't really need that one. Okay, so that's maybe slightly disturbing, but it's something that we should look into, certainly. What if we decrease the uncertainty? We had a better observation. So we've done this in a very hokey way. All we did was we cranked down the uncertainty, and we pretended we had the exact same observable. And we get a pretty big change in a lot of parameters that we would expect to see a change for boundary layer humidity. So this first one is sort of an entrainment parameter. And the other ones are related also. There's certain things like that we shouldn't see an effect, and they don't show an effect. So that's good also. And we also tried temperature. What if we had better observations of temperature? That has no additional difference. So we also learned that having observations of water vapor is much more important than having observations of temperature. So we can now report that to NASA and say, okay, this is what we want. So this is sort of a climate OSSI, a climate observing system simulation experiment. Similar to ones that are developed for data simulation, except instead of saying, I want to get a better forecast on short timescales, which requires state estimation, I want to get better projections of climate, which requires parameter estimation. So it's just a sort of very analogous extension there. Okay, now if we think about this also, I think there's another step that we need to take because, right, you can think about like, okay, I reduced uncertainty into parameters. Okay, great, yeah. Like who cares about that? Like 10 climate modeling nerds in the world, maybe, okay. Or you can start talking about reducing the uncertainty in observables, right? Some, liquid water path, and like, okay, how many people care about that? Like maybe like 100 climate nerds in the world. But really, like these things only matter to us, right? Really what we want to think about is quantifying this reduction in uncertainty in terms of things that like actually matter to people. So, equilibrium climate sensitivity, okay, yeah, that only climate nerds really care about that, but more people should perhaps. But things like heat waves or late frost, right? If you get a late frost, your crops are ruined. Your crops that you've just planted are ruined, and that has a huge impact. So, I think this is something that we need to do, kind of switch evaluation of our models in part from this sort of parameter or science or however you want to call it space to this sort of impact space. There's a preprint by Anne Fridland that's out there. I'm just going to zoom past this, so if you need to get that reference, please find me. Okay, so yeah, what actually matters, and you could put a value on this, right? $10 trillion value of better information about the transient climate response. So make sure to mention that next time you're asking for a raise. And we could also put it in terms of these things that have been defined in the impact space, climatic impact drivers. There's variables that sort of that we can pull from climate models that encapsulate those impacts. There's a whole flow chart into what things those are. I won't talk about that. And we've kind of played around with this a little bit and asked, yeah, if we had those better observations of boundary layer humidity, how would our equilibrium climate sensitivity change? And our uncertainty gets reduced, and the value also changes a little bit as well, which is a little bit interesting. This is cloud feedback, and then this is the ECS here. And Greg Sassana was doing some work on that at NASAGIS. Okay, and this all kind of fits into this pyramid that Kathy showed the other day, where basically we have our sort of model work over here in this slab here, where we're developing models, and this is sort of our knowledge of the system. We look at societal value, right? Those are sort of those impact drivers, and hopefully that leaches up here to public understanding. And then that feeds back down here to sort of these fundamental knowledge, these missions of NASA, right, that informs the next set of missions that we're collecting new information on. So hopefully this is a way of sort of stitching the line through this little pyramid that NASA's really cares about. All right, so switching gears a little bit right now. In theory, this is what I mentioned at the beginning, doing a physical model has an advantage that you should be able to sort of unify knowledge from different scales and observations, right? So we might hope that we have some way of basically doing this link, right, between sort of the observations, maybe some high resolution simulations, and our global models. This is what we'd like. And one of the sort of key uncertainties that we want to look at with clouds is precipitation formation. So this is something that Kate Loftus did for her PhD. It's basically a bunch of distributions that are undergoing collision coalescence. And you start off with stuff in the cloud range, and you get collision coalescence, and then it becomes rain, right? This is little droplets bumping into each other, becoming rain. All of these distributions would actually have identical evolution in most models. right? So most models don't see any difference between these distributions. They'd evolve them in the exact same way. And obviously, it makes a big difference, right? So there's sort of a lot that we're not capturing with the models that we have. And there's a lot of sensitivity there, right? You can see that a lot of them are pretty similar, but you get very rapidly different evolution. Okay, so we'd like to improve some of these processes. We want to use data, including sort of reference models that are a little bit better than our bulk models. And we've developed sort of an approach that does this. Again, I'm going to skip through. So we try to get rid of a lot of structural assumptions and then use data to constrain things. And we have some flexibility here that we can choose different physical structures. So we can choose whatever moments of the size distribution, where moments are defined this way, are best. We don't have to just use the traditional choices of number and mass. Okay, we get rid of fixed process rate functions. We use some functional base set. Okay, I said I was going to skip through the math, so I'm going to do that. And then we use Bayesian inference to estimate our parameters. Yeah, it's equations. We can match sort of traditional schemes. So here I'm just matching to 3 different traditional schemes, which is fine. That's not terribly interesting. We can also match to bin schemes. So depending on the structure of BOSS, so whether we make a 2-moment or a 3-moment version, whether we use 1 term for our equations, 2 terms for our equations, or we include a term that's range dependent, we can get better fits. This is sort of offline, directly trying to fit to the process rates that we see in this reference scheme, this fancy microphysics scheme. The interesting thing is that it doesn't make a difference once you plug it into a time-evolving model. So this is sort of time evolution of a one-dimensional column model. So we have time on the x-axis, height on the y-axis. And this is basically clouds evolving. This is the reference bin scheme in this column. This is one version of BOSS that has 2 moments. And this is another version of BOSS that has 3 moments. The 3 moments should be better. It's more complicated. It has more degrees of freedom. It seems to work better offline. And then when you plug it in offline and look at the difference between our BOSS and the bin, it actually doesn't really make a difference. The 2-moment and the 3-moment both look bad. So there's no advantage to a more complex scheme structure when using these sort of offline fits. That's interesting. When we tune online, though, we do see an advantage. So when we actually tune in a time-evolving sense, it does matter. So it matters where you're doing your parameter estimation. You can't just do like a fit offline. And I think there's some subtle reasons for this, which I don't have time to get into. But it's super important, I think, to do a realistic constraint because it's like, does your algorithm know what matters? You're giving it data. Does it know what part of that data is the most important data? No, it just knows that you've given it data, right? Some of it is like when the cloud is just forming, you're getting this nonlinear process that's happening really quickly. And then some of it's when like the rain's already established. It's not as important there. Yeah?
Does doing this online tuning process kill your time advantage a little bit in terms of speed?
You mean the speed of doing the estimation process? To a certain extent, yeah. But the main hurdle is developing that perturbed parameter ensemble. This is actually doing direct MCMC, but yeah, we've sort of moved on beyond that, and we're using this emulator approach. And yeah, there's an initial time sink, right, running 900 large eddy simulations. But it's not that bad, and it's certainly not as bad as doing direct MCMC on LES simulations, running 1 million simulations.
Or as doing a bin scheme at runtime.
Yeah, right. Yeah, I think the bin scheme would probably be around 30 or 40 times slower, so yeah. Okay, can we constrain parameters instead in 3D high resolution LES, right? So if a 1D model is, it's important, or it's better to do that than to do the offline, then maybe analogously, like we really should be looking in 3D, right? Maybe the things that matter in 3D, the data that matters in 3D, is different than in 1D. Will that play? No, it won't. Okay. All right, so yeah, just an image of a 3D LES. And so this is all being led by Kate Loftus. And yeah, so all credit goes to her. So basically the idea is the same. We have BOSS, a bunch of large eddy simulations with different parameter values. And so it produces different runs. This is actually kind of interesting. You can get situations where there's no rain. You can get some situations where there's some rain. And then you get some runs where it's all rain and there's no cloud. The rain's just, it's like the cloud turns to rain instantly and there's just, anyway, it doesn't make sense to me. Obviously, those would be ruled out. Those parameter values would be ruled out. And we constrain this with a reference scheme, which in this case is a bin scheme. Really, we should be doing probably Lagrangian schemes, but I won't get into that. And we use the same methodology here, and Kate actually was the one in our group who did this initial coding of basically doing this uncertainty quantification of the emulator. Okay, what do I want to say about this? What I want to say about this is we do these multiple iterations, and we get some slight change in the parameter distributions. It's not severe, but basically between the first round and the second round, we get some variation. That's just a detail. Again, this is making the point that our sort of instantaneous fits are going to look quite different than our time-evolving fits. So it's in quite a different part of the parameter space, which is a little bit interesting. We get good matchup to our bin scheme. So this is various aerosol values here on the bottom. And then this is sort of domain mean liquid water path. The stars are our target bin scheme. And the prior is this pink. And the posterior is this blue line. So yeah, and then, whoops, the rain rate is also pretty well matched. This is again saying that the online fits, which are these blue lines, fit a lot better to our target, which is these yellow lines, than either the prior or our sort of default scheme. So the default scheme is P3 in this case, which is the green line. All right, more plots that show that. Okay, what about structural errors? Things like the way that we have taken the size distribution and condensed it down to a few numbers to make our problem tractable, or the functional form of the rate equations. Well, one of the big structural assumptions in doing clouds is that you have a sort of two-category approach. So you have cloud droplets, and they bump into each other and become larger, and at a certain point, we just call them rain, right? At some point, we're just like, that's not a cloud droplet anymore, that's a rain droplet. And there's sort of a bunch of different processes that have to happen once you create two categories, right? I could have these cloud droplets bump into each other, and what they produce is a larger cloud droplet. I could have two cloud droplets bump into each other, and they become large enough to be a raindrop. Okay, so the first one is self-collection. The second one is auto-conversion, right? Cloud turning into rain. And then there's accretion, which is a raindrop hits a cloud droplet and becomes larger. All right, so what we've done is we've basically taken one physical process, which is cloud droplets bumping, or liquid droplets bumping into each other, and turned it into four different processes in our model, right? It doesn't make sense. And this threshold can be a sort of arbitrary thing. Like, what do you call rain? What do you call cloud? There's no real clear dividing line there. I will say there are reasons why that's done. I don't think people are stupid for doing it. But let's say that we just have liquid, right? Then we just have a single process, just collision coalescence. Does that make things better? Well, there's some research perhaps that suggests that it does. So Hugh Morrison has a recent paper where he's tested this out. I think Poulin will talk a little bit about what Hugh's done. Poulin's working with Hugh on this stuff as well. And then Arthur has also tested this out in three-dimensional LES. And one of the things that he's found out is that rain sedimentation works a lot better. And I think one reason for that is that if you just have rain falling, with a single category scheme, you'll have more prognostic variables describing it if you have a single category scheme. You'll have, well, okay. There are details there. I probably shouldn't get into it. I could talk a lot about that. There's also a recent paper by Kara Lamb using a sort of machine learning reduced order modeling, and she's shown some advantage there. Okay, so yeah, so details here, and this is why I sort of stopped talking in the last slide and didn't finish my sentence. Traditional two-category, two-moment schemes, we do cloud mass and number usually, and then rain mass and rain number. In the single category, instead, we have 4 moments of the full distribution. So we'll have total number and total mass, but then we'll also have these other moments. So the 6th moment is basically the drop size raised to the 6th power, and you integrate over the size distribution. That's actually related to radar reflectivity. So when radar send little waves out and they bounce back, it's related to that 6th moment of the distribution. There's also a 4th moment, and that's closely related to rain rate. So basically you have 4 variables, and you always have 4 variables to describe whatever the distribution is. So if you have pure rain, you now have 4 variables to describe that pure rain. If you have pure cloud, you now have 4 variables to describe the pure cloud. So that means you have 2 more variables in those cases than you normally have. When you have mixed cloud and rain, you have 4 variables, the same that you did before. So just from that sort of simple, overly simple argument, there should be an advantage. Yep.
How are the 6th and the 4th moments moved around the model? Because they don't map onto mixing ratios that follow the wind.
They are advected. They can be advected normally. There are issues with the advection. So there are numerical issues with the advection. So yeah, that's a detail that requires consideration. And there is actually numerical broadening associated with that. So yeah, that's a concern. Yeah.
There have been experiments looking at other, basis functions. I mean, we have the Lagrangian, you have the den. Has anyone looked at like splines as a, since this is kind of a
splines, I'm not sure. Actually, I think, is that what Emily de Jong is working on? I'm not sure. Emily de Jong's doing some interesting work on different basis. And so one of the things that she's been looking at is something in between a Lagrangian and a bulk scheme, where basically each Lagrangian particle has a distribution. So there are different methods. Kara's paper, of course, looked at a sort of latent basis for this. And I think somebody extended that work recently to be advectable. So yeah, there's a lot of work on this being done.
It wasn't spline basis, it was, you can use different kernel functions, radial Gaussian kernels.
Okay, again, skipping past the equations. They're not pure power laws anymore. They're a little bit different. Skipping the math. Okay. And the constraint format, the bottom line, basically you just need to read the bottom line. It's basically the same setup as Kate's large eddy simulation constraints. And again, we use this CPE methodology where we estimate the annular uncertainty and we do multiple rounds. So the multiple rounds are interesting, I think, here. If we just take the prior, we get actually something that sort of looks like rain. So the bottom is our reference. This is the bin model, and the top is boss. So we get something that looks like rain. This is domain mean liquid water content, liquid number content, 4th moment, 6th moment for the 3D domain with height. Okay. So we get something that looks okay. But then if we do 1 round of this CPE, we get something that's better. And then if we do 2 rounds, we get something that's a fair bit better. There's still some weird stuff here. So like in the 6th moment over on the right, I don't know what's happening here. Okay. The 6th moment here on the right, something looks a little bit funny with the reflectivity increasing with as you go down. So there's still some small issues there, but there's a lot of improvement. And to look at sort of the time evolution or line plots, this is the prior, again, number, liquid, 4th, 6th moment. The first round, it actually doesn't look like that much improvement, and then the 2nd round. So the sort of iterative method we've really found to be necessary. Yeah, I could talk about the sensitivity to aerosols. I'm going to skip past that. We can also compare it to 2 category schemes. I'll probably skip past that also. There seems to be some modest advantage to the single category scheme versus the 2 category scheme. One issue here is that it's hard to compare the 4th moment and the 6th moment because 2 category boss does not actually have 4th and 6th moments. You can compute that from traditional schemes, but not from boss. So, well, we could look at domain mean precipitation rate and see that sort of traditional schemes are a lot worse. Okay, I'll skip past that. All right, so that's great. We've sort of done a little bit of this, maybe, and maybe we need to do this part still, this part on the right, connecting to observations. So we've started to look a little bit at that, and basically one of the things that Kate is interested in is, this is work that again is being led by Kate Loftus in collaboration with Christopher Williams, who's a radar expert at University of Colorado Boulder. And basically using field campaign data and profiling radar Doppler spectra to do a retrieval of the drop size distributions to basically evaluate, is there evidence, observational evidence that, that the assumptions that are commonly made in schemes are a problem, right? We've kind of assumed this in the work that we've been doing, but is there observational evidence for this? So one of the cool things that you can see is that you can actually see processes happening. So this is altitude going down, and this is within cloud and below cloud, and these are size distributions, retrieved size distributions of the rain. And one of the things that you can see is going down, you get larger droplets. So that's collisional growth. That's pretty cool. And then also you can see that the whole distribution goes down. So it's not just the largest droplets that are growing larger. Below the cloud, the whole distribution goes down. That's clearly showing evaporation. So OK, we can see processes. That's nice. This is basically the radar curtain for that, that case. This is off of the coast of San Diego, or on the coast of San Diego, the EPCAPE campaign. And well, we can evaluate. Most parameterizations assume a exponential size distribution. So this is radius on the bottom, and this is basically number. And so the size distribution look like that, right? That's the shape of it in this space. What we find is actual pretty significant deviation from that. So just sort of taking this, and this is basically doing some sort of normalization so you see the shape of the distribution rather than the amount. You get something quite different. OK, does it matter? So one of the things Kate does is she takes these retrieved distributions and plugs them into Lagrangian microphysics column model to look at the processes that are happening. Does it matter? When we're looking at sedimentation of these droplets, when we're looking at evaporation of these droplets, do those assumptions matter? And they do matter. So if we just use the distributions, the evolution looks like this. So this is reflectivity and altitude. So the reflectivity is decreasing as these things evaporate. But if we make the assumptions that most models make, we get something completely different. And this has impacts in terms of precipitation efficiency. So that's the basically mass at the cloud base versus the mass at the surface. So does the rain that comes out of a cloud end up at the bottom? It also has a big impact on evaporation rate. So the assumptions are basically this one-to-one line. And what we actually get is something quite different. So this is sort of indicating key deficiencies in models shown by the observations. OK, all right, that's great. So now we've talked about this stuff on the right. We've talked about this stuff on the left. And then, but how do we do this sort of translation here in between? And this is sort of a pretty disturbing thing that we can't just take the parameters that we've learned here in high-resolution models and plug them in to our global models. So this is, why not? Even if you use the same microphysics scheme, even if the equations are the same, you take these parameters at high resolution, you dump them into the global model, and things go really wacky. I'm not going to talk about the reasons why, but yeah, it's a little bit scary. So what we do is single column models. So we take a single column here with forcing, some sort of prescribed forcing, and then we can run our global model with our global model physics, and then we can compare it to our high resolution of the same forcing. So high resolution model, same forcing as the global model. The global model is just a single column. This is high resolution though. And then we can do this comparison. And we can do this comparison for a number of different cases that are to varying extents informed by observations. All right, so Kate has been working on this. basically doing this comparison. And she's looked at some of the outputs of various variables, surface rain rate, for example, liquid water path. And she's looked at it for the single column model as well as for the global model, and then looked at what the LES says, which is pretty far away from a lot of these values, and then set up a little region for history matching. This stands for not ruled out yet. And basically done these tests. So if we include both the single column model and a global constraint, like how do those compare? And you can see in some cases there's very little difference between the global and the joint constraint. The SEM provides relatively little, and in other cases the SEM does provide different information than the global constraint. And maybe you have to look at that a little bit carefully. I think I'll just get past this. Oh, I'll just mention that Kate has also played around with doing a comparison between history matching, which is this sort of thresholding, right? I accept inside of this boundary and I don't accept outside of it, and the Bayesian Markov chain Monte Carlo. So we're looking at that because I think that does matter, and I'm not exactly sure how it matters. Okay, so conclusions. I'm actually going to skip past the conclusions and just talk about maybe some disturbing questions. So what does it mean to estimate parametric uncertainty in the presence of structural errors? I think it's like, we think that that's meaningful, but I don't think it is actually, or I think it needs to be questioned how meaningful that is, right? Our solution to Bayes' theorem is still conditional on all those structural assumptions in our model. So what do we get out of it is something that is, okay, it's correct according to the way we form that equation, but is it what we want, right? Do we want our parametric uncertainties to stand in for our structural uncertainties? Do we want it to be useful in that way, that like the spread in our model results from parametric perturbations includes that structural error as well, that we're not accounting for? I think that's a disturbing question. If parameter estimation for Earth system models is a null test for machine learning-based parameterizations, this is another thing that I've been thinking about. With NWP, right, the success of NWP, numerical weather prediction for weather, has been allowed for by data assimilation, the process of state estimation. It's been incredibly successful. Now machine learning models have come up, and they're whooping the traditional NWP models. Why? I would posit that a lot of the reason why is because data assimilation has never considered parameter uncertainty. Right? There's very few studies doing joint state and parameter estimation for weather prediction. So what I would suggest is that it would be nice if the field would start to look at joint state and parameter estimation in a sort of data assimilation framework. How much can we get from that? Is there sort of some ground that we can get from that? And I think one of the nice things there is that maybe we learn more about clouds that way too. How best do we leverage observations? So this is the question that came up earlier. Is there a middle ground between doing sort of climatology, just averages and stuff like that, and full sort of 4D data, right? There's a lot of data we throw out when we look at averages, but how much should we throw out? And then the one thing I didn't talk about, which is in the abstract, is stochastic parameterization. We're not wrong in the same way everywhere at every time. Right? We're wrong in different ways in different places. So if we really want to talk about like characterizing the ways in which our models are wrong, does it make sense to do that deterministically? Maybe not. And I'll end it there.